Hello everyone, we're back for part 3 of chapter 2, and in the previous video we went through and actually described how Newton came up with his method for taking derivatives with calculus and how we were going to take a number of those expressions and apply them to make what we are now calling kinematic equations. And so I'm just going to go ahead and write those three calculus ratios on the page here. We'll go ahead and expand the screen so we can see better. And we used the second equation here to produce one of the 5 kinematic equations. And so I'm going to put together our columns. So we had our first kinematic equation, which came out to be final velocity equals initial velocity plus acceleration times time. And this equation leaves out the displacement of the object. And what we're going to do in this video is we're going to finish producing the other 4 kinematic equations, and each of those 4 is going to be missing one of the other 4 kinematic terms. And previously we already used this equation right here, or at least we tried to, but we could not carry through with the math because we couldn't ensure that the acceleration was in fact constant, because the acceleration wasn't even a part of that expression. But even so, even if we did have a constant acceleration, the velocity could not be constant, and we wouldn't be able to carry through the integration, which is why we had to sneak over to the second equation, and that's how we produced our first of the kinematic equations. So now we'll try using the third equation in line, and that doesn't look quite as welcoming just because it's a second order derivative, but we can still approach this in the same manner as what we did with the previous derivation. We're going to start with the insistence that we have a constant acceleration. So that means that the ratio of our changing position to time is also constant. I am going to perform a separation of variables by multiplying each side of the equality by the second order time expression. And in doing so, we get acceleration and time on one side, and we have our position on the other side. And the next step is to start the integration process. And just like the previous example, we want to make sure that we carry out the integration as a definite integral so that we don't have to include any of those pesky constants of integration. And so we'll go ahead and assign limits to these integrals. The integral on the left is with respect to time, so we'll go ahead and use initial and final time values. The integral on the right is with respect to position, and so we will use initial and final position values. Now we do the integration. Well, I have one integral that is being applied to a second order differential term. And back in calculus, we learned that integrals were antiderivatives. So if I take a derivative and an integral at the same time, they basically cancel each other out. Well, I have one integral and two derivatives on the right. So what's going to happen is that one integral will cancel with one of the differentials, and it will leave me with a first order differential on the right, which then I'm somehow supposed to evaluate at limits. We'll come back and talk about that in a second here. Let's take care of the left-hand side. Again, I have one integral and a second order differential. So that one integral will cancel with one of the differentials, and it's going to leave me with a dt. But unlike the right-hand side, we do have a constant that comes along for the ride in this integration. And when we integrate a constant, the constant adopts the variable on that side. And just like the right-hand side, now we're expected to evaluate at our limits, but this is not something that we can actually do right now. Those limits of integration are actual concrete values, and I still have differential terms inside of the expressions, which tells me that things are still changing. So I can't evaluate at my limits yet. What I could do is I could do a second round of integration to get rid of those differentials, and that is in fact what we are going to do next. But if I can't evaluate at the limits after taking that first round of integration, then technically I am faced with the indefinite integral situation, which means that I have to incorporate a constant of integration. I don't have a choice. So we tried to avoid it, but during this first step, it's actually unavoidable, and so I'm going to have to add in a constant of integration. It doesn't matter which side we add it into, just as long as we've added in a constant of integration. Everything about the kinematics, if we look at all of these terms, to get from displacement to velocity requires a time relationship. To get from velocity to acceleration requires a time relationship. So everything here seems to be focused on the time dependency. So I'm going to go ahead and add that constant of integration to the side of the equation that is using the time variable. All right, so there's my constant incorporated into the expression. And now it's time for us to do a second round of integration. Once again, I'm going to attempt a definite integral, which this time will be successful because I have one integral versus one differential statement on each side. On the right, dx will integrate to x, which will have to be evaluated at our limits. On the left, we have two terms, at plus our constant of integration, that will need to be integrated with respect to t. And so that gives us at squared over 2 plus ct. All of that will need to be evaluated at our limits for time. And in the previous video, when we were working through this, we said let's be nice to ourselves. Let's let the initial time be 0. And that means that the final time will just be the generic time interval t. And so when we evaluate the left-hand expression at those given limits, nothing really changes. We still get AT squared plus CT, because if we evaluate the limits at time t equals 0, we don't get anything. So that's the left-hand side evaluated at our time. And then the right-hand side evaluated at our limits is x final minus x initial, but that's just delta x. And so we can shorthand that to delta x. And technically this would be our kinematic equation. I've gone through all the steps of the integration. I have an algebraic expression, but this equation is pretty much useless to us without knowing what that constant of integration is. We need to figure out what the value of c is equal to. Otherwise, there's no point in using this equation. So here's how we're going to do that. And this is going to sound completely counterproductive to what we've just done. But we're gonna take this equation that we've just produced, and we're going to take the derivative of it. And you're probably thinking, well, wait a minute, why would we do that? We just went through 2 rounds of integration to get here. Why do we want to go back? Well, keep in mind how we did the integration. As we were integrating each side of the expression with respect to the variable on that side. Now what we're going to do is we're going to take the derivative of both sides with respect to the same variable. And that variable is going to be time. So we will get a slightly different outcome from this. On the left-hand side, yes, we are literally stepping back into the math. When we take the derivative with respect to time, we get a t plus c. But when we take the derivative of the right-hand side with respect to time, over here what we have is the change in position, and we're shrinking everything down to that infinitesimal statement, which means that this is going to shrink down to an infinitesimal statement as well. We're gonna update this to what it actually should read, which is dx dt. But what is dx dt? Well, that is the instantaneous velocity of the object at any given time. And just to drive home that point, I'm going to label that as v sub t. So we have an expression here that tells us what the velocity should be at any given time. And that's also kind of useless because I don't know what the constant of integration is. Except up here we said, let's be nice to ourselves and let's let the initial time be 0. If that's the case, what do you get for velocity when the time is 0? Well, we get the acceleration times 0 plus the unknown constant of the integration, which means that our constant is the initial velocity. V evaluated at 0, well, that's the initial velocity. So now that I know what that constant of integration is, I can bring that back into our expression. And we have our next kinematic equation. This is the second kinematic equation that we're going to use. Again, it's all about getting our answer to match the book's answer. And really everything, the way it's written here is the way it shows up in the book. And so what we have is delta x equals v naught t plus half of at squared. So all I've done is I've rearranged the order that things were written in. But now we have to figure out where does this fit in with the columns up here. Every kinematic equation is going to be missing one of the terms. And this equation that we just produced is missing the final velocity term. So I'm going to place our equation right here. This is the equation that does not utilize the final velocity in any way. And now we move on to a third equation. So now we need to figure out how we're going to produce a third equation given the fact that we've discounted using this one and we've already used both of these. So now what do we do? Well, now is where we have to start getting inventive with the math. And when I say inventive, that doesn't mean that you can just do whatever you want. You still have to follow the rules of the mathematics, but as I said, we're going to get inventive with some of this stuff. I still can't use the first equation, but maybe I could reuse the second or the third equation if I were to alter them in some fashion. And since the second equation looks a bit more user-friendly, we'll try that one. Now, when I say alter, I still have to maintain the equality. So that means whatever I do to one side of the expression, I have to do to the other. Just like we were doing with the separation of variables. But if I do a separation of variables here, I'm just going to get right back to the same expression that we had before, and that's not what I want just yet. So another little trick that we can try with the algebra is I'd like to multiply one side of the expression by a value that won't change that side of the equation, and the only option of doing that is to multiply by a 1. If you multiply one side of the equation by a 1, you don't change the expression, you don't change the equality. But that's where the inventive part comes in. I'm going to multiply the right-hand side of this equation by 1. And here's how I'm going to do that. Dx over dx. Technically that is 1. And so I have not changed the equality. But I now have the product of two fractions on the right-hand side. And if you remember from your days back in middle school when we started learning about adding, subtracting, multiplying fractions, we just multiply straight across the top and bottom. So this example here would be 3/10. But is there any difference between that multiplication problem and that multiplication problem? And the answer is no. We can switch around the numerators or the denominators all we want. We're still going to get the same end result. And so that's what we're going to do up here. You can't change both the numerator and the denominator, otherwise you haven't changed anything. What we have to do is we just have to pick, do we want to switch the numerators or the denominators? And it really doesn't matter. I'm just going to flip a coin, and I will flip the denominators around. So we will have dv over dx, dx over dt. And the multiplication of those fractions is still going to result in the same outcome. So we haven't changed anything, except that now, right here, we have a ratio that we know. We have dx over dt, and dx over dt is our definition of velocity. So we can now write this acceleration term as we have dx dt, which is velocity. In fact, that's instantaneous velocity, times the rate of change of velocity with respect to position. So we've actually lost the time dependency from this expression. Now we have an expression that says that the velocity is changing with respect to position. Is that possible? Well, think about the last time you were in your car as you're driving down the road. Can your velocity change as you displace going down the road? And the answer is absolutely. Well, now we have a new expression that we can use our calculus on. I have three terms in here. We have displacement, velocity, and acceleration, and we want to try that separation of variables technique that we were using before. Now, everything on the right-hand side of the expression has velocity terms in it. So it looks like our best bet would be to multiply each side by dx. And remember, acceleration is a constant, but velocity is not a constant. Velocity is a variable. And this is where we have to be careful when we take our integration, because on the left-hand side, when we integrate everything, we will get the constant acceleration times x evaluated at our limits. But integrating the right-hand side, we're integrating the velocity with respect to itself. And the fact that we have dv in here expressly tells us that the velocity is a variable, and so we have to integrate it as such. So the integral of v with respect to itself is going to result in v squared over 2. And we will also have some limits in here. We'll use our generic initial and final for those limits. And now what we get is acceleration times, we have x evaluated at final initial, well, that's just delta x, equals, we have v squared over 2 evaluated at v final, minus v squared over 2 evaluated at v initial. And there's our third equation. But again, it's all about getting our answer to match the book's answer. So the first thing that we're going to do is we're going to multiply both sides of the expression by 2 so that we can get rid of the 2's in the denominators. So we have 2a delta x equals the squared difference of our velocities. And then we're going to add v naught squared to each side, which will result in v final squared equals v initial squared plus 2a delta x. This equation is leaving out the time. As such, we will insert it right at the bottom here. And there's our third kinematic equation. Now we still have 2 more that we have to make. And as inventive as this approach was, I don't want to risk trying to get 2 more inventive over here or over here. And so we're actually going to abandon the calculus approach. And since we have 3 variables that we've already produced, maybe we can just rely on the algebra from here on out. Maybe we can do a combination of two of the three equations that we already have to produce the other two equations that we need. In doing so, whatever combination of the equations that we already have, we need to make sure that we eliminate either the initial velocity or the acceleration from the expressions. So let's give that a shot. The first thing we need to do is we just need to pick two equations that we want to work with. And it doesn't matter which two equations we use. We just need two of them. Everybody always seems to be in love with the first equation just because it looks so user-friendly. So we'll go ahead and use that one. And then it's a toss-up between the other two. Maybe I'll use the third equation, the one at the bottom. So these are the two equations that we're going to use. And I need to figure out some way of combining these equations so that I can eliminate one of the two remaining variables. And it's at this point that I need to make a choice. Do I want to eliminate the initial velocity from each term, or do I want to eliminate the acceleration from each term? And again, it doesn't matter which one you go after, just as long as you go after one of them. And so I'm gonna go after the initial velocity. So I want to eliminate the initial velocity from these expressions. The easiest way to do that is to take each expression and rearrange it to solve for the term that you're trying to get rid of. And that might sound kind of counterproductive, but we'll see why this works here in a moment. The top equation, we're going to rearrange that to solve for the initial velocity. And to do that, I would just need to subtract the AT term from both sides. And so I would get V final minus AT equals V initial. For the bottom equation, I need to rearrange things so that I can get V initial by itself. I can get really close if I subtract 2a delta x from each side. That will give me V naught squared, but I need V naught. Now there are two choices that I can do at this point. I can try taking the square root of each side, but in taking the square root, we have to have two outcomes. So there's a positive root and a negative root. The other possibility is that I could go up to the first equation, and I could square both sides of that equation. So instead of having V naught, I have solved for V naught squared from each expression. Well, why would that be helpful? Because now I have two expressions that are equal to each other. I have V final squared minus 2a delta x equals the square of the quantity V final minus AT. And once I set those two expressions equal to each other, V naught is gone. It's no longer part of the expression. I technically have my fourth kinematic equation. But again, it's all about getting our answer to match the book's answer. We can actually clean up this expression quite a bit. which is what we're going to do now. So now the algebra continues. We have v final squared minus 2a delta x equals, and we're going to have to FOIL this binomial. In doing so, we will get v final squared minus 2v final at plus a squared t squared. Okay, so what can we do with that? Well, the v final squared terms will cancel out on each side. And what else do we have here? We have, if I move everything to one side of the equality, so I'll take the 2a delta x, add that over 2a delta x. What do we have? 0 equals a squared t squared minus 2v final at plus 2a delta x. And the reason I wanted to do this, it almost looks like we might have some kind of a quadratic expression, which in terms of time we do. However, each term in this expression has the acceleration present. And so we can go through and we can factor out the acceleration from each of those terms. And then our author really likes setting up the expressions in terms of delta x, or solving in terms of delta x. I don't know why, but that's just how the author of this book does things. And so let's take what we have here and let's rearrange things in terms of delta x. Let's solve things in terms of delta x. The first thing we would have to do is get rid of this 2. So if we go through and divide everything by 2, 0 divided by 2 is still 0. We would have half, oops, we would have half of a t squared minus v final t plus delta x. And so delta x would equal, we're gonna move the other two terms over by subtracting them over. If we subtract negative v final t, that becomes positive v final t. And if we subtract the 1/2 at squared, we get negative 1/2 at squared. So there is our fourth kinematic equation, and we were able to produce that simply by combining two of the equations that were already present. So we have delta x equals v final t minus half at squared. Now, do be careful and notice that these two equations are very, very similar. They have almost an identical setup, except that one of them uses the initial velocity, the other uses final velocity. One of them has a plus sign, the other has a minus sign. So make sure that when you come back to grab the appropriate kinematic equation for your homework, that you're grabbing the right equation. So that leaves us with one more equation that we have to make. We need an equation that leaves out the acceleration. And now that we've seen how things work, we can duplicate the approach for acceleration. And since we have these two equations already on the screen, we might as well make use of them and see if we can produce our fifth equation, which will exclude the acceleration. I'll make myself some room here by getting rid of some of this other work. All right. So I'm going to use the same two equations that we used before, except now I need to rearrange these for acceleration. The first equation, if I rearrange for acceleration, we have v final minus v initial, and then I will need to divide everything by time. So there is the acceleration in terms of the first equation. And then the second equation, I need v final squared minus v initial squared, all divided by 2 delta x. And that is equal to a. So now we have two equations that are equal to the same acceleration. We can now set those expressions equal to each other. And technically that would be our fifth kinematic equation. But as with all of the other examples, there is some cleanup that we have to do so that we can make our answer look like the book's answer. The first thing that I want to do is I want to get rid of those denominators. And we can do that by cross multiplication. I'm going to multiply the time from the left-hand side up to the numerator of the right-hand side. And likewise, I will multiply up the 2 delta x from the right-hand side over to the left-hand side. And what that does for us is it allows us to just work with terms that are in the numerator. So do be careful with the context here. Everything on the top needs to be multiplied by those values respectively. And now we need to see if there's anything else that can be cleaned up or factored out. On the left-hand side, we have v final minus v initial. On the right-hand side, we have v final squared minus v initial squared. And that is something that we should kind of recognize, because this is, back in algebra, what we called the difference of squares. So the difference is the minus sign, and we have our two squared terms. And the difference of squares could be factored down to a plus-minus combination of those terms. And the moment we do that, we see that we can actually factor out the v final minus v initial terms from each side. We don't need them anymore. And what is left, once again, our author is very big on having the final version of this expression written in terms of delta x. Well, there's only one thing we have to do to get delta x by itself, and that is to divide by 2. So we have delta x equals 1/2 of the summation v final v initial times time. And that is our fifth and final kinematic equation. So we will add that to our list. Delta x equals 1/2 v final plus v initial times time. So there is the list of the 5 kinematic equations. We have those matched up against the missing term from each equation. And now we can jump in and start doing all kinds of equations of motion with different objects. There is one thing that I want to comment on. At this point, in the book, if you're following along with the reading, the author actually gives a name to this last equation that we derived. The author calls this the average velocity equation. Now we've already had average velocity show up before. We said that average velocity was the change in position with respect to time. And the reason we had to call this average velocity was because the time interval was too large. We said that there was too much that could change during a large time interval, and so we had to call this an average. Well, that equation doesn't look anything like the average velocity equation that we came up with in the previous videos. And I disagree with what the author has done here in naming the equation as such. In my opinion, if one equation is worthy of a name, all of them should get a name, but I don't know what you would name the other equations. The reason the author calls this the average velocity equation, if you actually look at the equation, you can probably see why. You have inside the equation the summation of two terms, which are then divided by 0. So technically that would be the average of the two velocities, initial and final. And so you would be using the average velocity to solve for your displacement or your time, except there's nothing inside this expression that guarantees that your velocity is going to be linear with respect to your acceleration, unless that acceleration is in fact constant, which is not always a given, as we will find out in some future chapters. So I am not going to use this notation myself. I am not going to refer to any of these equations by a specialty name. If I do say average velocity, or if I have some kind of a homework question or a quiz question or a test question that refers to the term average velocity, this is the expression that I am expecting you to use. Alright, so now we have all of the kinematic equations. Now we can start using those kinematic equations for different physics problems. It is at this point that I would like to segue into a helpful little checklist. I usually provide this checklist to my students during the course of any semester. And this checklist is going to be the 10 steps for success with physics problems. And technically this could be for any kind of homework or test problem in any class. It doesn't have to be physics, it could be engineering, math, you name it. Other professors may have a similar step-by-step process. I've seen some that were 7 steps. I've seen some that were like 13 steps, but I think 10 steps is a nice round figure. And so consider that you are presented with some kind of a physics problem. So you're sitting down to do your homework one night. You have a problem that is presented to you. So what's the very first thing that you should do? Well, the very first thing that you should do is you should read the problem. I know it sounds like a given, but I've had plenty of people that just kind of skim over the problem statement, and if you don't read the problem statement correctly, you may be missing out on an important piece of information. And ask yourself, after you're done reading that problem, do I understand what it is that I need to do? So what to do. So do I know what to do? And if the answer to that is no, then you might want to go back and reread the problem statement. Read it a third time. If you've read it so many times that you have the problem statement memorized and you still aren't quite sure what to do, then it's time to seek some help. There are numerous links with Wiley Plus where we can click on example problems. There are simulations, animations. You can log into one of the office hours. You can seek help from the tutoring center if there are any TAs with the department that are offering some office hours or some tutoring. You can seek those out. Go ahead and check your syllabus, or you can contact me if you'd like to know what other resources are out there. But if we don't understand what it is that we're supposed to do, then what's the point in continuing with the problem if all we're going to do is just kind of trip over ourselves in trying to find an answer? So that's really the first step, is to read and understand what we are being asked to do. The second step, this is something that we can do at the same time as step one, and that is to list your givens. As you're reading the problem statement, there are going to be certain given pieces of information. And it's a lot easier if you can write those given values off on the side of a piece of paper, so you could very easily access those values on your paper instead of having to go back and reread through the problem statement. Step 3 can also be done along with step 1 and step 2. Draw something. A lot of these physics problems are going to involve objects that are moving around in different directions, positive, negative. It really helps if you can have something on the paper that you can visualize, especially if you get stuck and you need to seek help from your professor or a tutor or a TA. If you can put stuff down on paper that you can show to someone else, it makes it a lot easier to track down where the mistakes might be. That, and if you can put more stuff down on paper, that's less stuff that you have to try to keep track of up inside your head. Step 4. Once you have something drawn in your system and you have all of your givens listed, take a moment and label everything inside that picture. So this is kind of a combination of steps 2 and 3, but you want to have absolutely as much information as possible in front of you so that you can take the next step towards the mathematics. Step 5, now that you have everything drawn and labeled, choose a reference frame. And the reference frame is really just there to determine what the positive and negative directions in the problem are going to be. And I've had some students that say, well, my other professors say that the reference frame should be the very first thing that goes into any kind of diagram. And I can agree with that to a point. It's very important that you have the reference frame there so that you know what the positive and negative directions are. But there are also some benefits to waiting until you can see the full picture laid out in front of you, because there may come a point where you have a physics problem where almost everything is pointing in the negative direction. If we had just waited until the problem statement was done, maybe we could have chosen our reference frame to point in the direction that everything in the picture was pointing in, and then we could have a whole bunch of positive terms to work with as opposed to negative terms. And I'll show you what I mean by that when we do a couple of these example problems. Step 6. So now that we've read the problem, we have an idea of what's supposed to be done. We've got our drawing ready, our reference frame. Now we want to produce the equation or equations necessary to solve the problem. Now, I use the word produce because in physics, and this is going to sound weird, but in physics, every problem is unique. As such, we need to make up the equations needed to solve the problems every time that we do a physics problem. So, saying we're going to make stuff up as we go sounds kind of bad, but that's exactly what we're going to be doing. We need to produce the equations that are necessary to solve these problems. For right now, well, what did we just spend a whole lecture period doing? We produced the equations of motion. We do not need to go back and reproduce those equations every time we do a kinematics problem. They're already there. Really, all we need to do is just go back to the list and pick the one that is appropriate for the problem that we're trying to work. We've already produced the problem, so step 6 is already taken care of. Maybe a better statement would be to choose the equation necessary. But we haven't produced every equation possible yet. There are still going to be more situations out there with our physics problems that may require us to produce a different equation, one that is not currently on the list. And so step 7, once you've chosen the necessary equation to solve the problem, do yourself a favor and rearrange the equation to solve for the needed value. You have all of these kinematic equations up top, and let's assume you're working a problem that involves the very last equation on the list, and it's your job to use that equation to solve for the displacement of the object. Well, that equation is not currently set up to solve for the displacement of the object. We would have to rearrange that equation, and this would be that final equation rewritten so that we could solve for the displacement. And the reason that we want to rearrange the equation is so that we're not constantly having to drag all of those given values through the math. If I were to take an equation and plug all the numbers in right away and then have to rearrange things, there's a much better chance that I'm going to make a mistake in the algebra as I rearrange those numbers. But if I leave the equation in general form and then plug in my values after the equation has been rearranged, then I'll have a better chance of reaching the correct solution. So step 8 sounds pretty obvious at this point. Now that the equation has been rearranged, we will plug in the given values. Step 9, solve. We'll say solve for solution with units. Don't forget your units. And well, that seems like the end of it. You know, we have our answer, we have our units. I thought this was a 10-step process. So what could possibly be left for step 10? Well, this is where we want to go back and check our work. Time permitting, go back and check your work. And there will be ways that we can check the work with these problems. So now it's time. Let's try a couple of kinematic problems using the equations that we have circled up top, along with following the 10-step process that we have here. All right, so let's go back to the stoplight. And you're sitting in your car at the stoplight. Light turns green, you hit the accelerator. You accelerate at a rate of 2 meters per second squared for 10 seconds. And I'm going to assume that this is the positive x direction. So just following along with the 10-step process here, I've drawn a picture. I've indicated the given parameters. In this case, the given information would be the acceleration and the time. I've chosen a positive direction for the system in this reference frame. And so now I'm pretty much at step 6 already. I've just cruised right through those first 5 steps. These steps actually go pretty quick once we get used to them. And so now I have to choose the appropriate equation that will allow me to solve for something. Well, I haven't even asked what I want us to solve for yet. So let's find the value of the final velocity at the end of the 10 seconds, and I also want to know how far the car has displaced from the stoplight during those 10 seconds. Now, for the kinematics, we have a little something that I like to call the rule of 3. So, given 3 pieces of information, so pieces of information, you can solve for the remaining 2. You can solve for the other 2. And the reason for this is because each of the kinematic equations only utilizes 4 terms. So each of those equations, I have to have at least 3 pieces of information that I can plug in, and I can solve for the 4th unknown. But we said that we can solve for the other 2 unknowns. Well, how are we going to do that if each equation only involves one unknown? Well, that means you're going to have to go and pick a different kinematic equation to use, but we can do that. So here we go. I need two different kinematic equations to help me solve for the final velocity and the displacement, but that means I need three pieces of given information. And again, it only looks like I have two, except part of the problem statement says that we're at a stoplight. So that implies that we have an initial velocity that is equal to 0. And that is our third term. What I like to do is, anytime I have any kind of kinematics problem, I just like to list out the 5 variables and see, oops, I had delta x in there twice, and just see what information I have. I already know that the acceleration is 2. I know that I have a time of 10 seconds, and I know that the initial velocity is 0. So there are the 3 givens. I now need to solve for the remaining 2. Which one should we solve for first? Well, it looks like we've got the final velocity written down first, so using my 3 pieces of given information, I need an equation that involves those 3 along with the final velocity, which I'm trying to solve for, which means that there's no room for delta x anywhere in the expression. So we go up to our list of equations, and which equation leaves out delta x? Well, very quickly we can look at our missing column, and the equation that is missing delta x, that is the first equation. So I'm going to grab that first equation, and as it turns out, it's already set up to be solved for v final. So in our 10-step problem solving process, we are at step 7. We want to make sure that the equation is rearranged for the value that we're solving for. I'm going to get rid of this just for the moment so that we can plug in our numbers. Step 8, plug in your givens. 0 plus 2 times 10. Step 9, solve for your answer with the appropriate units. We have 2 times 10 is 20, and the units of velocity are meters per second. So there we go. There's our final velocity, and I'm going to go ahead and squeeze that in here. Now we need to solve for the displacement. Now here's something interesting. In our list of kinematic variables or values, I now have 4 pieces of information. And the kinematics says I only need 3. So does that mean that I can go through and just pick and choose any 3 of the 4 values that I want to use? And the answer is yeah, technically you can. But keep in mind that this is a value that we just solved for. This is a value that we just calculated. How confident are you that that is the correct answer? Because if you take that and try to use it to solve for the next answer in line, if this answer is incorrect, then the next answer is going to be incorrect as well. So the best thing that we can do at this point is continue to work with the values that were given to us. I still have these 3 as my given information. Now I want to solve for the displacement, which means that there is no room for the final velocity. So we go back up to our list of equations. The equation that leaves out the final velocity, that's the one right in the middle. So I will bring that equation down here. Delta x equals v naught t plus 1/2 at squared. That equation is set up to solve for delta x, so I don't have to do any rearranging with this one. At some point in the future, we will have to rearrange an equation, but it doesn't look like today's the day. Step 8 says plug in all your given information. Initial velocity of 0, time of 10, 2. We have an acceleration of 2 and 10 squared. We get 0 for the first term, 2.5 cancel out, and 10 squared is 100. 100 meters is how far this car will go during its acceleration. Okay, we have our two answers, so I guess we're done, right? Well, time permitting, we can check our work. Well, how do we check our work for two answers that were found independent of one another? Well, now is where we're going to take those two answers of 100 meters and 20 meters per second, and let's plug both of those into a single kinematic equation that we haven't used yet. So we've used the first and the third equations. So let's pick an equation that we haven't used yet. Let's go with the last equation in line. So V final squared equals V initial squared plus 2a delta x. Let's take that equation, we'll plug in our answers for V final and delta x along with the other two values that show up in the expression, which are V naught and a. So in this case, there's no place for the time. If we can plug all of these values into this equation and get a true statement, then we have our method of checking our work. So here we go. Moment of truth. Final velocity squared is 20 squared equals initial velocity squared, 0 squared, plus 2 times acceleration times displacement. On the left, 20 squared is 400. On the right, we get 0 plus 2 times 100, which is 400. Yep, that's a true statement. And so I am satisfied that we have the correct answers for both of those. If you're still not sure, go back and take another kinematic equation that we haven't used yet and plug your answers into that. But there's almost always going to be a means in which we can go back and we can check our work to make sure that we have the correct answers. As far as the homework goes, the online homework is going to tell you if you have the right answer or not, because it will highlight your answer in green. But on a quiz or a test, if you have the time remaining, it is well worth your effort to go back and check and make sure that your answers are correct. All right, I'm going to end the video with that. We will have one more video with the Chapter 2 material, and that is primarily going to be example problems using the kinematics. Specifically with falling objects. We need to talk about how we're going to use gravity as a constant acceleration in these kinematic problems. So I'll see you then.